Finding the equivalent resistance of this circuit. Okay, so first I'm going to assume the question is, what is our equivalence of AB? I know they're supposed to be lowercase. I don't care. You can understand the point. So first thing is we want to, this is drawn in a confusing way. We want to draw it in a less confusing way. So first, A and B are up here, but I'm going to put the A over here and B over here because it's all connected by a wire. It's assumed that the wire resistance is 0, so you can just move it wherever you like. Next thing we're going to do is we're going to try and redraw some of this. So the way I approach these circuits, when you can solve it by parallel and series, as opposed to having to use Kirchhoff's voltage rules, I just like to redraw it a whole bunch of times. So this one is going to be, we're going to assume that this one is 55. And then we got these guys down here. The question is, well, how do we want to redraw them? Well, you can connect any two lines. So you can jumper these lines like this. So I can draw it like this, like that. And so now it looks more like a traditional, I guess, parallel resistors. And the idea here then is, since there's no resistance to these lines, we can draw them however we want, as long as they're connected to things that are also 0 resistance between them. So this is going to be the equivalent of something kind of like this. Whoop, whoop, whoop. Click, 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 clack, click, click, and then they'll all be connected. Get a different color here to accentuate the differences, or what I'm writing here. So this is going to be 75, this is 40, this is 50, this is 25. And so these are the same drawings right here. If you look at it here, these two resistors on the left side are both connected. So if you look and say, yep, they're connected. They're also both connected to the 55 and 100. So yep, connected to 55 and connected to 100. So all the connections are the same. This is just more visually appealing. So now that we got this, we're going to find parallel equivalent resistances here. So we have 1 over 40 plus 1 over 75 equals 1 over our equivalence. This is the basic formula you're going to use for combining resistors in parallel. So simplifying this slightly, we'll have 40 plus 75 over 40 times 75, common denominator, is 1 over our equivalent. So therefore, our equivalent, I see how I went from capital to lowercase? I should stay more consistent. Equals 40 times 75, just flipping the top and the bottom, over 40 plus 75. This gives us a calculator. Well, it doesn't give us a calculator, but we take the calculator. 40 times 75, click, divided by quantity. 40 plus 75. I know it's 115, but I'm still going to do it just in case. Okay, and we get 26.087. 26.087. And one good check here is when you have two resistors in parallel, the equivalent resistor should be slightly lower than the lowest one you have. So it should be higher than half of the lowest one, but it should be lower than the lowest. So what I'm talking about here is, as a dummy check, so the combined resistance, or the equivalent resistance, should be greater than half of the smallest, so greater than 20, it is, check. But it should be less than the smallest one, less than 40, which it also is. So it's good. Same thing over here. I'm going to skip to kind of the punchline here, where we do 25 times 50 over 25 plus 50. So that's going to be, I don't know what 25 times 50 is. I should know that. I don't. So 25 times 50, that seems reasonable, divided by 75, which is 25 plus 50, and that gives us 16.67. 16.67. Makes sense again. It's greater than half of 25, which is 12.5, but it's less than 25, so that also seems reasonable. And these are all both measured in ohms. And so then I'm going to redraw this circuit once again. Usually when I'm solving circuits like this, I redraw them a whole bunch of times. And it's usually pretty messy, but that's just because usually when you're doing homework to train for a test, and tests are generally time sensitive, and you're not given as many points for good handwriting as you are for correct answers. Correct answers within the time limit. So we got here, we have second one right there. Okay, so what we did is we converted this one to 26, right there, converted that one to 16. We have a 55, and then we have 100 up here. Is it 100? Probably 100. So we're going to combine these two in series. So we're going to rewrite this one more time. And we're going to have 100, 55, and we're going to have, get the calculator, plus 26.08695652 excessive. 26.0, 26.087. 26.087. No, that doesn't seem right. Doesn't seem right at all. Wow. Plus 16.666667. There we go. 42.754. 42.754. And like, wow, this is incredibly messy. Indeed it is. Okay. So now we have these all in parallel, and we have 3 resistors in parallel. So now we're going to do the same thing we did before, except now we're going to do it with 3 resistors. So R equivalent will equal 1 over 100 plus 1 over 55 plus 1 over 42. And it's really 42.754, et cetera, et cetera, et cetera. You got to be careful what went around on these. And this will be 1 over R equivalent. Now the rule of thumb I had before, where it's greater than half the smallest but less than the smallest, that doesn't apply with this because you're doing with thirds. It should be greater than 1/3 of the smallest, but also less than the smallest, because we're doing 3 terms now instead of 2. And after you do a whole bunch of these kind of problems, you're like, okay, I kind of see the pattern. So actually, I should make sure that's actually 100 ohms real quick. Come back here. Yep, 100 ohms. I'm going to say R1 is 55. Come back here. Take a deep breath before I do a whole bunch of calculations. So 1 divided by second answer, that's the 42, plus 1 divided by 100. I know it's 0.01, but I don't trust my mental math. Plus 1 over 55. And now I should be able to take 1 over this answer. And I have 19.39. So R equivalent equals 19.39 about ohms. So to backtrack what we did real quick, coming all the way back over here, past the multiple drawings. So first thing you do, redraw into something that looks semi-sensible. You can, any point on a line is equivalent to any other point on a connected line, because they're all wires, there's 0 resistance between them. That's how I justified moving the A over there, B over there. Then I could redraw it like this, which looks more reasonable. From there, I then combined the resistors in parallel into equivalent resistances. Whoop, came down here. Forgot this guy right here, so I drew him in. So I had now 2 resistors in series. I then combined those. And then I had 3 resistors in parallel. And I used the R equivalent equals, I guess I should make this an arrow. There we go. I did 1 over each, add them all together, took the inverse of that, multiplicative inverse, and I got my final equivalent resistance. And that's how I would approach this kind of problem. Big idea is know how to do series, you just add them together, and then know how to do parallel, which is you're adding reciprocals and then taking the reciprocal of the result. And the big idea then is draw a whole bunch of pictures every time you update the circuit. Hope that helps. See you next time.